So today I'm going to introduce the topic of static friction to you. Basically what we're going to cover in today's class is we're going to look at friction, different types of friction, and we're going to look at some important characteristics of static friction and with some examples and free body diagrams. So let's actually start with a very simple example that you've seen before in class. A box resting on a surface, something like this. What are the different forces acting on this box? Can you call that out as I draw the free body diagram for this? So considering the box to be a point particle, I have the normal force acting up there, and what other forces? Yes, the gravitational force acting down equals mg, and according to Newton's second law, the net force in the y direction should be equal to mass times acceleration in the y direction. But is there any vertical motion here? No, the box is actually in static equilibrium. So acceleration is 0. Putting all these forces together, I have the normal force up. See how I've chosen my coordinate axis, positive y up, minus mg, negative sign because it's acting down. So Fn equals mg. So you can see that the normal force balances the gravitational force, and the box is at rest there on the table. It's in static equilibrium. Nothing new there. You've seen this before. Now, if I were to push the box, right, give it a slight push, the box moves, it budges from where it was, it moves, it slides on the surface, and eventually comes to a stop. Let me include my force of push here, then ask you this. Why doesn't the box slide forever? Why does it come to a stop? Because there is some kind of a force that's opposing my force of push, that's opposing the sliding motion of the box, right? That force, that opposing force is the friction force, which we are going to discuss today. Friction is a necessary evil. Why is it necessary and why is it evil? It's necessary because it's because of friction that you are able to walk without slipping. Otherwise, we would all just be slipping and sliding. And objects are where they are because of friction. Otherwise, they would just be sliding. And why is it evil? Because friction causes wear and tear. When objects are not stationary, when they are sliding over one another, then also you have friction. Like this box, when it was sliding, it eventually came to a stop. So when surfaces are in contact with each other, what happens is when two objects are sitting on top of each other, they are like cold welded. So there are these bonds forming between the two materials, and when they start to slide, there is the breaking of these bonds takes place, and that causes wear and tear. So however flat the two surfaces may appear, if you look at them microscopically, atomically they're not actually flat. There are these contact points. So you see these contact points, there are these contact points between the surfaces that actually gives rise to friction force. Now let's take another example where you have a cabinet on the floor, resting on the floor, and you want to slide it from where it is, move it from here to the other corner there. What do? You push the cabinet. Cabinet doesn't budge. You push harder and harder and harder, and eventually there comes a point when you're able to overcome that friction force and get the cabinet to budge, and then it starts sliding across the floor. So when you're pushing initially, it doesn't budge. The friction force that's opposing your force of push, that is the static friction force. Static, as the name says, is the friction force that comes into play when two surfaces are stationary, when they are at rest, when they are not moving. And then eventually when the cabinet budges and starts to slide, then you have kinetic friction coming into the picture as there is relative motion between the two surfaces. And today we are going to look in particular at static friction force and some important characteristics of static friction force. So as I told you, you push harder and harder and harder, and the static friction force is going to oppose your force of push, which means that the greater you push, the greater is going to be the value of static friction force. So it assumes a range of values until eventually your force of push is able to overcome the maximum static friction force, and then the cabinet begins to budge or move. So what is this maximum value dependent on? It's dependent on how hard the cabinet is pressing on the surface. So what is the force here that gives you an idea of how hard the surfaces are pressing against each other? That's right, that's the normal force. So greater the normal force for two surfaces, for an object, greater is going to be the static friction force that you will have to overcome to get the object to move or slide. So if you look at the static friction force, it is proportional to the normal force there. And physics, you can remove the proportionality and introduce the proportionality constant, which is mu suffix s, Greek letter mu, that is known as coefficient of static friction. And experimentally, people have found out the value of mu s for different surfaces in contact. So this is basically an empirical formula. And they have recorded this value of coefficient of static friction for different surfaces. So whenever you have two surfaces in contact, right, like this box resting on a surface, there are two forces that come into play. One is the normal force, which is the perpendicular force, perpendicular to the surfaces in contact, right? And then you have the friction force, which is the parallel force, or the force that is parallel to the surfaces in contact or tangential to the surfaces in contact. So you have the normal force there, and then you have the parallel force, which is the friction force. And so these are the two forces that are coming into the picture when two surfaces are in contact. Now, I want to explore the relationship between these two a bit more, taking another example, which you've already seen before, of an inclined plane, right? And then I have a box there. So, as long as the inclined plane is flat and the box is resting there, it's not moving, right? As soon as I increase the angle of the incline, what happens? Is the box sliding now? No, it's not sliding, it's still staying there. Why? Because the static friction force is preventing it from sliding. And when it starts sliding down, what is actually causing it to slide down? What force? Component of gravitational force. So as I go on increasing the angle of incline at a particular angle, see the box begins to slide down. At about 30 degrees here, I see the box begins to slide down. So at that angle, the component of gravitational force along the incline is able to overcome the maximum static friction force and the box begins to slide down. Until then, the static friction force goes on increasing and increasing to balance the gravitational force along the incline. So let's actually draw the free body diagram for that and find out the maximum value of theta at which the friction force is maximum. So I have the normal force there, and I have the gravitational force down. I'm going to choose that as my positive x and positive y, and this as positive x. And this is theta from trigonometry, you know, that's the angle of the incline between y direction and mg. I'm going to resolve mg into its components, x and y component. That's the y component, and that's the x component, mg sine theta. And when the box is in static equilibrium, all these forces are balanced. I'm missing a force here. What's that? That's right, that's the static friction force along the incline, right? All these forces are balanced. So in the x direction, I have the static friction force balancing mg sine theta, gravitational force along the incline. And then in the y direction, I have the normal force balancing mg cos theta. Now if I'm going to divide one by the other, I have static friction force over the normal force, mg sine theta over mg cos theta. Mg gets cancelled out, so this is tan theta. And if I want to find out the value of theta, then I need to know the ratio of static friction force and the normal force. The ratio of that is basically mu s, which is tan theta. So I can find out what is the value of theta at which I can get the maximum static friction force. So if I know the maximum value of theta, then I can find out the maximum value of static friction that I will have to overcome for the box to slide down. And you can also see one important thing here, mg gets cancelled out, which means that whether the box is lighter or heavier doesn't really matter here. The value of theta for this particular surface is going to be the same. The maximum value of theta is going to be the same irrespective of whether the box is heavy or not. So earlier we saw the box slides down at about 30-degree angle. Now if I'm going to make the box heavier, let's see at what maximum angle it begins to slide down. That happens around 30 degrees again. So this is telling you experimentally as well that for maximum value of static friction, it doesn't really matter how heavy or light the box is. What matters is the two surfaces that are in contact, the materials that are in contact. So from the coefficient of static friction between the two surfaces in contact, you can find out the maximum value of theta at which maximum static friction which you have to overcome in order for the box to slide down. So with this we will stop and we will continue next class.